today with Professor Rony Keppens. He's here in Tenerife for the Solar meeting in Puerto de la Cruz, and he has gracefully accepted to come here today. Professor Keppens did his PhD while working at the High Altitude Observatory. He was working on the interaction of P-mode with solar spots. Then he moved. He got his degree from the KU Leuven in 1995. For a year, he moved to Freiburg to the Keppens Institute, still working on solar physics. And then he moved to the Netherlands to the Plasma-Physics Institute, where he worked on massive parallel computing, and that's where he got in touch with the AGN jet propagation problem, which he's going to talk about to us today. And then he became a professor in the Utrecht University in the Center for Plasma Physics, which is where he's working right now. And with no further delay, please, Rony.
Okay, so indeed it is my pleasure to be here. It's actually my second time on Tenerife, but the first time I managed to somehow only see 2 streets in the neighborhood of this. And I regret it very much because meanwhile I kind of enjoyed the scenery of the island. What I'll be talking about today is some of the latest work that I've been doing in close collaboration with my postdoc, Zaccaria Meliani. And the topic is relativistic hydro and magnetohydrodynamic models for jet propagation and deceleration, and in particular those jets in association with active galactic nuclei. So as a brief outline of my talk, I'm going to motivate the whole topic. Very briefly remind you, I guess, about some of the basic of AGN jet physics. And then very swiftly, I'm going to move on to the actual model I'm assuming. I'm going to take a special relativistic magnetohydrodynamic viewpoint on these flows, and I'm going to do the approach numerically, and I'm going to tell you a bit about our software and some of the features that actually are necessary in order to do these highly relativistic flows properly. I'll then grasp a few of the knowledge from the observations. In particular, I'll briefly remind you about the Fanaroff-Riley classification schemes and also explain what this HIMORS acronym stands for. And that will be the motivation for the actual results that I'm going to show you. There are a few pressing questions that come from the AGN jet physics and our understanding of them today. And in 3 exemplary studies, I'm going to tell you about how we can understand some of these jet physics. So I'm going to do relativistic hydro jet simulations and make connections with this acronym, HIMORS. I'm going to then move on to relativistic 2-component jet simulation, and I'll try to explain what I mean by 2 components. And I'll end with helically magnetized relativistic jet simulations. So the motivation, very briefly, jets are ubiquitous phenomena in astrophysics. We have here a radio observation of this particular radio galaxy 3C296. The galaxy is actually not immediately seen in this picture. It's sort of in the middle of this view here. And what is immediately prominent in this view are the prominent jets that are squirting out from the center of the galaxy. In the center of this galaxy, we have actually strong evidence for the presence of a massive black hole. In typical AGN context, these massive black holes can be of the order of 10 to the 8 solar masses, surrounded by accretion disks. And then by some means, not all the matter makes it, is accreting straight to the center, but some of the matter is diverted along the rotation axis of this accretion disk system, and is then squirted out in jets, which are most prominently seen here in these radio maps. The jet lengths are enormous, parsec to megaparsec. The fact that we see them in these radio maps is in fact a direct evidence for the presence of magnetic fields, because this is interpreted as a non-thermal synchrotron emission of relativistic electrons spiraling about magnetic field lines. And the basic ingredients that we know are playing a key role are also here in this, sort of artist view on the right, where we have, so the accretion disk system with a central black hole. By some means, some material is diverted into these jets. We have magnetic field lines that probably help to collimate these jets over these long distances. And the bulk flow of these jets happens to be relativistic with Lorentz factors of the order of 10 or so. Those being the basic aspects of AGN jet physics, I'm going to immediately tell you that I'm going to have a particular view on these jets. In fact, I'm going to, in this particular talk, not really deal with how this material eventually ends up being diverted into these jets. I'll just briefly sketch about that. In fact, most of the models that I'm going to show you today are going to assume a special relativistic viewpoint, so I have to stay away from the central black hole, obviously. I'm going to typically start at, sort of 1 parsec or so away from the launching region, and where everything can be dealt with in a nice flat Minkowski spacetime. Makes life slightly easier. The basic conservation laws that I'm going to handle are just expressing the fluid viewpoint that I'm having on these jets. So I have particle tensorial energy momentum conservation, and as soon as I incorporate magnetic fields, I have to deal with the full Maxwell's equation. If I do ideal magnetohydrodynamics, some of the viewpoints are just going to do special relativistic hydrodynamics, and then I do not take the Maxwell's equations along. If I deal with the Maxwell's equation, I'm actually also going to make an additional assumption, namely that I can take an ideal viewpoint on it, in the sense that in the co-moving frame, I have a vanishing electric field, which means that if I choose a particular Lorentzian reference frame, I can meaningfully talk about 3 velocities that you might be more familiar with if you're just used to classical fluid dynamics, where you have a 3-velocity vector, a 3-velocity electric and magnetic field, and then this relation expresses what I mean with vanishing electric field in the co-moving frame. In that same fixed Lorentzian reference frame, it is then convenient also for the numerical approach that I'm going to take a space-time split such that the basic laws that I have to deal with are just a set of conservation laws in the appropriate variables, one of them being this 3 magnetic field vector. In these laws, I'm not going to show you all the details, I can later on, but the basic, all the relativistic effects that you know about are taken into account. For instance, the fact that there are the length contraction effects. So lab frame densities and densities as viewed from another particular Lorentzian reference frame, they have this volume change effect due to length contraction. And all these things are embedded in this conservation law nature of this. I'm going to also do a numerical approach, and for that I'm going to handle these extreme contrasts that we are going to handle in these relativistic flows. And in combination, I want everything to be physically correct, in the sense that I want obviously positive rest mass densities, positive pressures, positive energies. I want velocities less than the speed of light. I want, hence, the Lorentz factor, which I indicate with this symbol gamma here, to be always greater or equal to 1. And I want, if I have a magnetic field, also a magnetic field that obeys Maxwell's equation, the divergence of B equal to 0. So these are constraints that actually put quite stringent demands on the numerics and the accuracy. And for that, it turns out that even if you're just doing one-dimensional relativistic flows, the necessity for some adaptivity in your numerical approach will be vital. And so the AMR stands for Adaptive Mesh Refinement. All of the simulations that I'm going to show you today are actually exploiting this in a key fashion. Without going into much more detail, I can refer you to some of the publications where we have explained in some detail some of the modules that we have embedded in our code. In fact, we can do relativistic hydro and relativistic magnetohydro by picking up the appropriate physics module in our software, but we can also do classical hydro, classical magnetohydrodynamics, etc. So it's a grid-adaptive framework. It's fully parallelized. It has this block AMR approach for those that are familiar with adaptive measure refinement approaches. And as we are going to deal with highly shock-dominated problems, the schemes that we have incorporated here are all of the shock capturing variety with various reconstruction procedures that have a certain amount of order of accuracy associated with them from second to third order. One of the standard test cases by now, in order to go on and simulate the more advanced flows that I'm going to tell you later on, is a test case that, in essence, reproduces earlier results, in particular results originally produced by Marty and collaborators and later on by different groups, where the basic approach of these dynamical studies of relativistic jets is to have, in essence, a jet dynamically injected from one side of your domain at a particular Lorentz factor, here a Lorentz factor 7 or so, with a certain density contrast between this injected jet and the uniform medium in which it is injected. If you do that and then you propagate this jet for quite some dynamical times, then you get typically pictures like these, where we have the overall, obviously you have a bow shock configuration that is separating basically the shock material from the unshocked external medium. You have the contact discontinuity where we have a lot of dynamical instabilities forming and leading to backflows, Kelvin-Helmholtz instabilities that lead to, in essence, a fairly turbulent cocoon. And we have then the jet beam itself, which is here the central axis of this particular view on this on this jet, where we have also internal shocks, these diamond shocks, etc. This is just to show what kind of pictures you can typically associate with these jet studies. For us, it was a test to reproduce these kind of results. That was a relativistic hydrodynamic test case. Our software is also handling these magnetic fields in a proper fashion. And so one of the tests that we have, in essence, designed ourselves is a relativistic variant of what is in classical magnetohydrodynamics known as the Orszag-Tang test problem. In fact, what it does is a very idealized problem. It's a 2D configuration. We set up a vortex that is supersonically rotating. In this case, it's actually rotating also relativistically. And then what this vortical flow does is it starts on the top of two magnetic island configurations, and it's wrapping those islands into each other. So here, you see here a later view of what this configuration does. I'm just going to try and show you an animation of what this evolution actually shows. As we start to wrap these islands into each other and we have full periodicity top and left, we actually get the squeezed islands that are heated up and that then basically lead to shocks that interact with each other. These shocks then, in essence, basically you have the formation of current sheets that are formed here on the diagonal sides of our domain. These current sheets in turn become unstable as a result of continued compression effects to what is in magnetohydrodynamics known as a tearing mode instability. And this is, okay, a test case that is taking the limits of the numerical accuracy to quite some degree, in the sense that here I just demonstrate that in order to capture the details of these shock fronts and then the actual instabilities happening within the compressed current sheets accurately, you need this adaptive mesh refinement. And here is just a view of the adaptive mesh, which is evolving in time, of course, as a result of the evolution itself. In relativistic numerical simulations, we also have to make do with proper equations of state. In fact, most of the simulations that I'm going to be talking to you about will assume a so-called relativistically correct ideal gas prescription. That means that as you normally have the specific internal energy being related to the ratio of pressure over density with a factor which is incorporating the so-called polytropic index, in a relativistic correct gas, that polytropic index is in essence something that must depend on temperature. As you go into the classical regime, so the sort of the cold temperature, so to say, that relativistic, that polytropic index is just assuming the constant 5/3 ratio for a monoatomic gas. But if those, the temperatures or the fluctuations themselves become relativistic, then in reality you should approach the polytropic index being 4/3. That is important because this polytropic index is actually also playing a key role in the compression ratios at shocks. And so it is not something that I just put in there for fun. It is really to capture the physics of these shock-dominated flows accurately. Our software is grid adaptive, and it is also parallelized. Here I'm just showing two representative scaling experiments where, as a function of the number of processors, we just run the same problem over and over again, just faster. Here, this is a domain decomposition experiment where we do a classical variant of this Ortzak-Tang problem, which I just showed you a relativistic variant of. And it's just to say that if we just use this software as a domain decompositioner, then we can achieve these kind of simulations in less than 5 seconds by just exploiting on the order of a few tens or so processors. If you go to the more demanding kind of simulations that I'm going to be showing you later on, then we can meaningfully exploit even more processors. In fact, we have demonstrated sustained 80% efficiency on up to 2,000 processors in full dynamic AMR simulations. With that being said about the software, I'm now going to try and explain to you what are the actual problems that we are going to address. And the motivation comes from this Fanaroff-Riley classification, which dates back to 1974, where at the time they were looking at the time, the best available radio maps of various galaxies and their surroundings. And these are just two examples of 3C449 and 3C47 here. And they, by doing a sort of this statistical sample, they noted that one can correlate the overall radioluminosity of these radio sources with the relative positions of where the low and where the high surface brightness in these radio maps are. So here, in fact, the center galaxy is actually supposed to be here, and then we have here obviously the most intense radio radiation coming from the nearby regions here, while in this particular case it is actually opposite. We have here a one-sided jet, actually, again, evidence for relativistic motion, and then we have here the most prominent emission coming from the faraway hotspots. By doing this in a statistical study, Fanaroff and Riley introduced this class 1, class 2 transition, which happens to explain that it turns out that these radio sources typically fall in these two categories, and they are separated by an overall luminosity at a particular radio frequency. So the FR1s are on the whole brightest near the core. So here is for 3C31 again, more modern image. Here we have again the center of the galaxy. We have here the jets, which appear in typically 80% or so of these FR1 galaxies. These jets themselves, they start out relativistic at the parsec scale. They on the whole become more diffuse and subrelativistic at kiloparsec scales. The FR2s, this is a typical galaxy in Cygnus A here, which is in the FR2 category. The emission, the central galaxy is supposed to be here, and then we can clearly see that the most prominent emission is coming from the lobes, from the hotspots, and this energy is actually transported there by means of very narrow, highly relativistic jets. So there is clearly a relation between the radio appearance of these galaxies and the way these jets actually transport energy and deposit energy in the intergalactic medium. Obviously, nature is never that kind to stick to a classification that people thought of in 1974. So, meanwhile, the HIMORs, or so-called hybrid morphology radio sources, have also been studied in quite some detail. These are galaxies that have an FR1 appearance on one side of the galaxy and FR2 characteristics on the other side. So here is a particular example of that, where we can clearly see an FR2 type lobe with a hotspot to the southeast of this galaxy, and then there is a more diffuse jet to the northwest, which is more typical for these FR1 type problems. As you might argue that the jets are ultimately responsible for transporting the material and the energy out, it is quite likely that the source here would yield identical launch conditions on both the top and the bottom side of the accretion disk system. So in some way, this very existence of hybrid morphology radio sources can actually be a positive argument in favor of a role for the ambient medium to actually quickly decelerate highly relativistic jets, in particular the highest energy FR2 type jets, on one side of their galaxy by means of differences in the ambient medium with respect to the central source. So the AGN jet challenges that I'm going to address are actually directly coming from these overall fairly global statements that I have collected thus far on FR1, FR2 galaxies. A major problem is how can we decelerate highly relativistic flows? They carry lots of energy, especially the FR2s. So, well, as I suggested so far, these HIMORs, the very existence of these hybrid morphology radio sources, suggest that a possible candidate to induce effective deceleration is the external medium. Another topic, which I will also address, is, well, it can also be an internal effect, in the sense that one of the issues that I'm going to explain later on is that this very source region may have conditions that launch radially stratified jets. And it is these radially stratified jets that I'm also going to be studying later on and introduce to you. And I'm going to show you that we have found that such radially stratified jets are actually subject to internal dynamics, to internal instabilities that may effectively cause the slowdown by means of internal mechanisms. And then the fact that these jet flows are on the whole magnetized is something that I'm going to be showing you by addressing the role of helical magnetic fields in collimation and propagation of relativistic jets. So, having this basic special relativistic hydro or magnetohydrodynamic view on AGN jets, there are not a whole lot of parameters that actually determine how I should set up my simulation. In fact, I have to just take the overall observationally established values for the overall jet kinetic energy and then somehow impose these in my simulations. Also, doing these simulations at the proper Lorentz factor of order 10 or so, 10 to 20. And then my parameter that I can play with is ratios between the jet and the intergalactic medium inertia, and in essence the density contrast. And so the first type of study is actually going to assume that here we have this jet injected, we have a symmetry axis. Well, in reality we don't quite have a symmetry axis, but I'm going to assume it nevertheless. And then we have a sort of dynamically injected jet, which may or may not have a certain opening angle, and that is then propagating happily through intergalactic medium, which may or may not be itself stratified. We can then look at what happens if such jets encounter additional contact discontinuities along their way. The fact that these jets traverse over these enormous distances means that they are inevitably running into regions of differing influence, and so there have to be various contact discontinuities on their path. So with just an idealized study, I'm going to look at how such density differences have an effect on the overall deceleration of these relativistic jets. I mentioned before this effect of the varying polytropic index. This is important in this study because, again, as I mentioned before, the fact that the polytropic index can vary from place to space, whether or not the internal state is relativistically hot or not, affects the compression rate, the shock strength, and hence the overall propagation characteristics. So what I'm going to simulate is jet propagation through these layered media. I'm going to take an overall jet kinetic energy, which is of the order of 10 to the 46 ergs per second, and Lorentz factor of order 10, as I said before. And then here is a snapshot of just the zoom on the jet head, the tip of the jet, just before it encounters that additional density contrast that is posed by this density discontinuity further down in the path. And I deliberately here just through a zoom, I show the effective polytropic index just to show that indeed this jet, this highly relativistic jet, sweeps up intergalactic medium in front, and the state of the matter there in that swept up shell is actually relativistically hot. And that in itself can and will have a certain effect on the overall propagation characteristic. Sure. I have the diagram right here, actually, but this is sort of in a as soon as essentially the effective internal temperature becomes close to the speed of light. That's sort of the overall variation. Here, this diagram actually tells you exactly where this dramatic changeover is. I should translate that indeed to a Kelvin. That's a very good question. This preformed jet head then penetrates this other medium of a different density, and then depending on the density contrast that it encounters, its further propagation down this medium can be dramatically different. In fact, here I just show two, again, zooms of the overall configuration. Now I'm showing the logarithm of the rest mass density, where we can clearly see that the density contrast is a defining parameter. That was already something known from these simulations where we just do traversing jets in uniform media. And so the density contrast actually is the key parameter in whether or not this jet transits to a sort of more turbulent, lobe-dominated cocoon, or does it propagate happily on as a fairly stable beam with sort of knot formation. The key point is that the density contrast is something that essentially triggers the overall transition from, again, relativistic to non-relativistic states. We have explored the differences between low and high energy jets. I'm just going to show you a simulation here of one where the overall characteristics are such that this jet starts off as an FR2 jet in the overall energy values that we have imposed. Then it encounters this density contrast here of a certain value which is well, fairly high, of the order of 100 to a few hundred. And then we have the dramatic changeover to propagation dynamics, which is more associated with the FR1 type jets. So you can see here that there is quite a bit of the energy actually being sent back into the original medium that it traversed, and so that also has an effect on the overall deceleration properties. Again, depending on the overall density contrast that these jets run into, we can have jets that, well, as they start off at FR2, then they just happily carry on, or not. And so the key feature is, maybe not too unexpectedly, the overall density contrast that these jets run into together with their Lorentz factor. And one of the things that we did also vary in these studies is whether or not these jets start out as either cylindrical or more conical jets, on the scale of this visualization, it is perhaps a bit hard to see, but these jets is something that starts more conically in accord with sort of the overall opening angles known for these relativistic AGN jets. And then again, that also has quite a bit of effect on the overall dynamics and how all these internal shocks then are then generated and interact with the external medium. So by doing a series of these kind of dynamic jet simulations, so the basic result that we were trying to address is how strong a density contrast does one really need to actually be able to decelerate a jet that starts out with FR2 characteristics to one with FR1. And so here is a collection of essentially the position of the jet head as a function of time for all the 10 models that we have pursued. And these are the ones that start off as the FR2 characteristics. Here they run into the external medium, this contact discontinuity. And again, the defining parameter here is just how strong the density contrast is, on top of the fact whether or not we assumed in these media a further density stratification in accord with density falling off as one goes away from this central region. And so you can see that we did manage to get jets transiting fairly abruptly to jets that are on the whole traveling with speeds that are quite alike these FR1 type jets, and then being decelerated to speeds that are for all intents and purposes, subrelativistic at kiloparsec scales. Details that we can address with these highly dynamic and highly high-resolution simulations is what happens here at this interface where we are actually triggering classical instabilities as well. We have a shock that essentially runs into a contact discontinuity that is known to trigger Richtmeier-Meshkov instabilities. This is in essence the deposition of velocity shear that happens on this on the shocked contact. That in turn leads to Kelvin-Helmholtz instability development. This is known as Richtmeier-Meshkov, and here we have all the details that are associated with that, which we can study separately. On the computational side, they are all high resolution, grid adaptive computations, typical resolutions of several thousand by several thousand. We took various refinement levels. Computations, we need about 4 days per day on 64 processors per case that we studied. This was an idealized study where one of the topics that I promised to address has been looked at, namely the external medium influence on the deceleration of these jets. A second effect that we have been studying meanwhile is internal stratification effects. So the AGN jets and the observations are bringing more and more evidence for this. If you look at these AGN jets in different wavelength bands, then you find that the high energy is giving you evidence for fast inner jet components, and then the radio maps show the so-called slow, well, still relativistic, but slower than this inner jet, outer jet. How can that be? Well, in essence, all the material is somehow being launched from the central region, and there is good reason to believe that there are indeed two components somehow being launched from these central regions. One, which is more spread out and associated with the disk, the accretion disk, that somehow manages to lift off some of the material in these jets, and one which is presumably driven by more general relativistic mechanisms coming from the central engine itself and the way GR mechanisms can tap the energy of these rotating black holes, for instance. So a generic mechanism for jet launch has been studied in quite some detail in the context of also young stellar object, but also compact object AGN jets. The basic mechanism is sort of visualized here in this, in fact, a classical MHD simulation. The accretion disk is sort of indicated here. We have two field lines that have been visualized, and as we start off with straight magnetic field lines that are pervaded in the accretion disk, they are being wound up. Now, the details of how this particular thing happens is that within the accretion disk, ultimately, the Lorentz force, the torque, actually, acts to break the material within the disk. At the interface of the disk external medium, in fact, we can set up one can realize conditions where the magnetic torque, so the phi component of the Lorentz force again, actually acts to spin up matter. So material can actually be diverted and start off on here this red streamline path. Some of the material actually starts in spiraling happily and being accreted, but about 50% of the material doesn't just go straight to the center, but goes into the regime where it starts to scratch the surface where the sign change in the magnetic torque happens, and then it actually becomes magnetocentrifugally accelerated in these jets. And the fact that this happens in twisted magnetic fields helps to collimate this material further out. And so the basic ingredients are just the presence of an accretion disk, and so the gravitational action of the central source, the presence of an overall large-scale ordered magnetic field, and then the physics of accretion and the Lorentz force, which inevitably causes some of the material being diverted up in these jets. This is a pure magnetocentrifugal launching mechanism. This is the Blanford and Payne mechanism. There are other models that have to do then more with sort of the radiation pressure and the overall geometrical configuration of jet. But personally, the main ingredients for this are also observationally quite well established, especially in young stellar objects, where the detailed observations of the near source jet stratification are all gradually bringing in more and more support for the overall magnetocentrifugal launching mechanisms, at least acting there, and by extrapolation here, also in the context of AGN. That being said, for how material gets launched from the surrounding accretion disk, I mentioned before that in order to have two components, there is still the central engine, which I haven't essentially mentioned too much yet. The fact that there is a central massive black hole, general relativistic mechanism, in particular the Blanford-Genaic mechanism, which in essence extracts the rotational energy from the black hole, can cause a very fast rotating inner hot jets. And so the overall here is sort of the artist view of the kind of models that I'm going to demonstrate to you later on. We believe there is this accretion disk and the central source region. There is good reason to believe that there is a slow outer jet component that is being launched by some magnetocentrifugal mechanism in combination with dynamically important magnetic field. And then there is a fast inner jet. And what I'm going to show you now is that the very presence of these two jet components means that if you take a cross-cut through this jet configuration, you actually are confronted with an interface between these two jet components that is, in a sense, again, liable to all kinds of either relativistic or non-relativistic instabilities in turn. And this is the kind of topic that I'm going to address right now. In fact, one of the things that we have come across very recently is now what I'm going to show you are simulations that are happening within a cross-section of these jets. And so you should envision that the main kinetic energy and the main motion is obviously perpendicular to the plane that I'm going to show you. There is an inner component that is traveling at about 30 or so Lorentz factor, and then there is an outer component which is relativistically colder, and that is traveling at about at a Lorentz factor of a few. And then depending on how we distribute this overall jet kinetic energy of 10 to the 46 Hertz, which is the number that I've been stressing so far for the overall jet kinetic energy, how we distribute this relatively over this inner versus outer jet may actually trigger or not centrifugal Rayleigh-Taylor modes. I'm going to show you an animation where in this particular case we actually have, so these two jet components. This is, in fact, a visualization, again, of the proper density as a function of time. And what you should see here is, first we had some interface instabilities developing, but now we have this prominent Rayleigh-Taylor type. So if for those of you familiar with just hydrodynamic simulations of classical Rayleigh-Taylor, we have the mixing of high density into low density as a result of gravity. This is precisely the kind of instability that is causing this intricate mixing of these two component jets. And as time progresses, and hence as we go further down the path of these jets, we actually have complete mixing of the inner with the outer jet component. And I'll quantify later on how that translates into very efficient deceleration of the fast inner jet. In fact, here is then a simulation of, well, here is the end state of a case where we just varied the distribution of the overall jet kinetic energy of inner to outer. And in this particular case, or for the same time, we have still a clearly pronounced fast inner jet with the overall outer jet. Of course, there is also some instability development here, but not as dramatic as in this case where we do trigger the centrifugal. Here is yet another case which is sort of intermediate between these two states that I'm showing you here, which is liable to all kinds of instabilities. Here there are these Kelvin-Helmholtz instabilities happening here. There is also Rayleigh-Taylor type instabilities happening here. But these instabilities remain of the more Kelvin-Helmholtz type variety. They never really give rise to these very pronounced arms of these Rayleigh-Taylor type finger modes that completely invade the overall inner jet. And while you can argue that this is clearly not a stable jet configuration, I fully agree, but over the whole time interval that we have here, the conditions are such that we can always speak of a fast inner jet component and an overall slower outer component. And this is also, if you diagnose these, well, fairly turbulent evolutions as a function of time with global parameters, this is also what is confirmed by doing those quantifications in that sense. What I'm arguing here is that depending on this relative division of the energy over the inner versus the outer jet components, we can argue for the relativistically enhanced Rayleigh-Taylor mode. In fact, we have also derived from linear hydrodynamic or linear magnetohydrodynamic equations in special relativity an approximate dispersion relation where you plug in essentially an exponential time and spatial dependence, and then you get a dispersion relation quantifying the relation between the temporal versus the spatial growth. And the key point to note is that in doing so, you find that in essence you have the contrast in what happens to be the effective inertia between these two jet components. This is also to be expected. In fact, classically, if you think away all the relativistic effects, so you set the Lorentz factor essentially to 1, and then in essence this H, which is the enthalpy, is just sort of saying that you should only retain this term because of the high amount. We just have the density contrast here between these two jets. This is exactly what you expect from a Rayleigh-Taylor type instability, where if you have gravity pointing down and you set high density on top of low density, then the high density will mix into the low density material. Now, the key point to note is here that the stability of this configuration in relativistic context is actually exactly opposite to what you would assume from this classical case. And the reason is that now in the relativistic case, we have this sort of boosting effect by means of the square of the Lorentz factor multiplying the density and then the enthalpy, and then also this additional possibility for having effective inertia added by magnetic field presence. The reason is that in our configuration, what we actually have is basically a cold outer jet, a hot inner jet, and then with the overall centrifugal force pointing outwards, that is classically stable, but relativistically, as a consequence of this boosting, unstable. So there is no classical counterpart to this mode, but it is a purely mixing mode that is only present if you have this two-component relativistically stable jets. And so here, what we then actually have done is we have run various cases where the initial conditions are just differing in how we distribute the contribution of the inner to the outer jet over to add up to the total kinetic energy flux. And we know from the stability criterion which should lead to this Rayleigh-Taylor mode and which not. And indeed, all our simulations actually show that. Here is then sort of the evolution of the Lorentz factor, the inner jet Lorentz factor, as a function of time. And in all these cases here, we clearly have a deceleration of Lorentz factor that start off at 30 and go below 10 over the time interval simulated, versus those two cases that we have designed from the beginning not to be liable to this instability. And indeed, while there is obviously also instability development, some mixing happening, it is not as dramatic as in those cases where we do find this relativistic enhanced Rayleigh-Taylor mode. So we can, it is not just the overall dynamics, so the overall deceleration in Lorentz factor, it is also the overall appearance, because here what we quantify is, again, for all these jet models, as a function of time, now the sort of the overall jet radius. So we saw that some of these actually start to spread out more radially as a consequence of all this mixing and all the angular momentum redistribution due to all these mode developments. And again, here we have clearly the distinction between those cases that are and those that are not liable to this instability. In the context of FR1, FR2, we are therefore speculating, or actually fairly confident, about this role being central. If there are indeed these two components, and as I said, the observations are bringing in more support for radially stratified jets, then depending on how the kinetic energy is actually distributed over the various two components, they are going to be liable to the instability further down their path, and hence become decelerated, yes or no. These were simulations that I've shown you, cross-sections in the plane perpendicular to the actual motion of the jet. You can, of course, be skeptical and say that the real thing is 3D. Okay, so we have to do a few things more. We have to go and see whether these 2.5-dimensional simulations, where I just assume that everything is invariant in the direction perpendicular to the plane, still holds in 3D. That is what I'm going to show you today. There are, of course, other things that we still need to do. These are preliminary results where I can show you here the distinction between these 3D two-component scenarios. I'm just going to show you the visualization of the movies. Here is a case where we have set up the configuration such that it is liable to the instability development, and you can see here clearly how the jet is completely distorted and in the time scale simulated becomes so decollimated and so essentially slowed down as a consequence. This particular case was then set up to be, in essence, stable to this relative for the same time interval. Okay, there is, of course, still quite a bit of mode development, still quite a bit of shear, but on the whole of the simulation, there is always a clear distinction between the presence of a hot inner jet and a cold outer jet. And so again, this confirms that these scenarios that we have addressed for the first time in these 2.5D simulations are very central and key also in 3D, despite the additional development of course, modes that know about the axial variation, that have to do with shear flow and that the development of Kelvin-Helmholtz instabilities in the axial direction. But the main evolution, as I was trying to explain to you here, is driven by this newly discovered Rayleigh-Taylor mode. Obviously, we need to work further, produce synthetic radio maps to actually make the link with the observations more direct. As a final point, I wanted to mention an aspect that in the simulations that I showed you so far, I haven't actually incorporated yet. We have incorporated magnetic fields in some of these simulations thus far, but as yet I have not yet dealt with helical magnetic fields. These simulations then we have been performing the propagation studies of helically magnetized jets, and those jets again have then a stratification at the inlet where we actually again dynamically inject these jets, in this particular case in higher density media, where there is a stratification that is reminiscent of having a central hot spine and then a sort of more gradual surrounding like these two component jets. But in this particular study, what I'm looking at is how the presence of a helical magnetic field, quantified here by the ratio, essentially the pitch of the magnetic field, as throughout the jet radius, how it has an influence on the propagation dynamics of what I'm going to be taking as kinetic energy dominated near equipartition jets. So near equipartition being that the magnetic field has at least as important a role as the overall thermal energy. And so here, these are then snapshots of, again, the jets are dynamically injected here from the side, and then we have followed their propagation into uniform but magnetized media. What I show you in the top is a visualization of, in essence, basically the location of where the strongest magnetic fields are, where we have the wider shades. So we have here, obviously, the whole jet beam is helically magnetized, and then you can see the backflows and the protrusions where we have sort of vortical flow development that propagate into the cocoon. They are also carrying the most dominant magnetic fields. In the bottom panel, I'm actually showing again the proper density, and you can see here how these protrusions are also the locations where we have the low density regions. So a flow analysis then shows you here in the top panel for the same simulation. In fact, the regions where everything is locally supersonic, and that's of course throughout the jet beam and at the head of the expanding jet. And then we have here also that the rotational motions in these that are basically being gradually shed from the recurring formation of the termination shock and then the contact discontinuity there is also the location of highly twisted flows. So I'm going to show you here just an animation of how we can then, with these kind of simulations, show how the helical magnetic field, how it is actually effectively transported down the beam as the beam penetrates gradually into this uniform medium, and how you can see here, if you study these movies for quite some time, then how you can see sometimes recoil events happening, and how we have local variations of the magnetic field twist, which turn out to be exactly happening at the locations of where we have then the formation of these internal cross shocks. So here is an attempt to actually quantify that. This is then the Lorentz factor near the jet axis, basically as a function of the distance along the jet. You can see here the location of the various internal cross shocks. Here is then, not exactly at the axis, of course, where it vanishes, but somewhat away from the axis, the location of the helical magnetic field component. And there is a good correlation between where each time when there is such a cross-shock being formed, we actually have also, as a result of the Rankine-Hugoniot conditions in relativistic MHD, enhancing of the helical magnetic field. As soon as you have more twisted magnetic field, that actually helps to pinch the flow and reaccelerate the material downwards. And so we actually have a sort of self-guiding effect due to this helical magnetic field topology. So also these are adaptive mesh refinement simulations, so we can zoom in on particular the jet head. This is then the location as a function of distance, again, location of the last internal shocks, and then the detailed variations of all the parameters that we have in our model, density, Lorentz factor, pressure, etc., that we can compare and then see in detail what are the 2D effects that we have in these simulations as compared to just the overall 1D equivalent of just something injected at high speed into a certain medium of a certain density difference. So we can we have studied the transition of what if these jets are, for all intents and purposes, not quite as relativistic. So here the overall Lorentz factor of this particular case is much lower than the case that I have been showing you repeatedly now. And here in this particular case, this is then almost a non-relativistic jet. What I'm showing here is how, again, we have the transport of this magnetic field, helical magnetic field down the beam, the enhancement of the toroidal component at basically the position of these shocks, and then how that toroidal field is effectively transported down and is then located in those regions where we have all these protrusions. So here again, what I'm showing here in the left panel here is actually the locations of this twist quantification, the quantification of the twist, and everywhere where it is black, it means that the toroidal component is actually the dominant component. So you can see here how the overall magnetic configuration is quite well transported down the beam. Then you have here at the location of the frontal shock, the termination shock, you have the formation of strong toroidal field, and that is then being transported down in all these vertical patterns. We looked at propagation characteristics, varied the overall topology of the magnetic field, and how this then translates into head positions as a function of time. Because of this radially stratified Lorentz factor inlet, which was very highly relativistic of the order 22 or so, varying to 4, the overall propagation characteristics are more due to the central spine rather than to the overall mean Lorentz factor flow. We then did try to make contact with what are the observational consequences for these kind of helically magnetized jets, whether or not these jets are purely poloidally or purely toroidally, and then everything in between these helically magnetized jets. How does the appearance in sort of synchrotron emission would be able to distinguish more toroidal versus more poloidal field configurations. And we have then basically just taken the direct outcome of our simulations, which is we have a quantification, a local quantification of the flow, the magnetic field, the angle between them, and then we can then produce these kind of synthetic synchrotron emission maps. But I should say that this is really a first attempt to actually get more meaningful observational predictions out of these simulations. We explored various variations in the thermodynamics. There is, again, as also the hydrodynamics, a strong influence of the density contrast. One of the key points is how, as a result of these rich cross-shock patterns that form in the jet beam proper, we actually have this continuous magnetically aided reacceleration of the flow due to the formation of more stronger toroidal field zones that pinch and help to accelerate the flow. These were, though, non-3D simulations. These were axis symmetric, so constrained in that sense, and we would need to revisit these in order to make contact with some of the simulations that we had before. With that, I have shared basically all I wanted to introduce you to, with some of the latest relativistic hydro and magnetohydrodynamic models that we have come across. I explained to you how we made contact with these hybrid morphology radio sources by actually looking at the effect of external medium, in particular highly relativistic jets running into pre-existing contact discontinuities, and how we can, from that point of view, argue how these external media can influence the jet propagation characteristics in a fairly dramatic way. Internal jet stratification we have looked at by means of these component simulations, and again there the FR2 versus FR1 distinction and propagation is by extrapolation of our dynamical fluid simulations, something that is also related to the very source region itself and how it manages to distribute the overall jet kinetic luminosity over these two components that are believed to be then propagating further distances. And I showed you how the presence of helical magnetic fields can help the reacceleration of these jets and hence explain the nice collimated properties and the propagation distances that we see in this. Here are some references, and with that, I'd like to thank you all.
Okay, we have time for some questions. Please remember that we are streaming live the talk, so do not speak without the microphone or they won't hear you. So, any questions?
A very, very exotic, very exciting set of simulations. So
thank you.
I have many questions, but probably I can postpone most of them for the coffee break. But I have a couple of them. I'm sure you are aware that these jets has been proposed to explain the coupling between the evolution of the supermassive black holes that are present in probably most of the galaxies and the galaxy itself. That's the way in which. So I have a question about whether these jets are able to sweep the external medium. I mean, whether they can be, the kinetic energy is enough or whatever to sweep the whole material around the jets. And something that is related to this other question is about the time scales. The jets that you have been modeling, you are like modeling the first stages of the jet when it is switched on. The time scales at which the jets crosses a whole galaxy at the speed of light is very, very short compared with the time scale at which the AGN is living. So I presume that for most galaxies, it's the stationary state what matters, not the beginning, not the launch of the jet, but what comes after. I don't know, not 1,000 years, but mega years or so.
Right. Well, as regards to your first question, basically the overall topology that is so typically coming out of these simulations is as a result of the sweeping up of the material as it progresses through. So the jet beam is, perhaps I didn't stress that enough, always fairly narrow, of the order of half a parsec to 1 parsec or so is the typical jet beam radius that we took. And then what I'm actually showing is how the region that we actually then see influenced by the propagation of this jet beam is most prominently forming this overall cocoon, which has quite a bit of extension. And as time progresses, it indeed is the most visible and the most extended region that is visible in these simulations. So to put numbers on this, I think I actually have to relate to your second comment, because although these are simulations that at least can compete with some of the simulations produced by other teams that actually look at the dynamics of these jets with high-resolution simulations, they indeed go to timescales that are way too short to actually match with the megaparsecs that I've been talking about. That is a constraint that we can still simply not address with the kind of simulate, because what we do here is simulations that traverse on the order of several tens to up to 100 parsec or so. What we actually would need and would like is how does this extrapolate to the overall megaparsec scale. Now, what these simulations do reach are end states that, at least in terms of the overall mixing properties and the overall propagation dynamics, have reached a certain stage where, with some confidence, although maybe not 100%, but we can claim to be, representative for the further sweep up. Basically, what will happen is that the front of the bow shock and all this downflows and all the vortices that are being formed there are just sort of making their way through and just adding more and more turbulence to the overall cocoon. It is sort of, perhaps it's not the right word, but in a self-similar fashion, you can extrapolate this to the distances. But you're absolutely right. If you really look at the numbers that we are doing here, although it is the best that we can do on supercomputers now, it is orders of magnitude short of the real thing. That's a good question. How well? Well, I guess a safe thing to say is that we could design from the overall parameters that sort of, if in essence, go into these models, more appropriate models for these systems too. And I'm fairly confident that some of the aspects that we have touched upon, like how these relativistic jets sort of propagate and the various shock patterns and the various instabilities that these jets are liable to, are quite likely to come out in those scenarios as well. Now, at the same time, what we did here was fairly specific, taking the overall ballpark scenarios for the AGN jet physics. But as I'm sure you realize, we just start up at a certain distance from what we then believe to be the launching region, and then how the jet has already reached a certain stage, and then we looked at propagation. And in that same sense, we can apply it to the systems that you mentioned. But I would be more hesitant in the physics that actually then is associated with the regions closer to the launching region, which I have not quite addressed here in these simulations.
But in your motivation, you have very clearly said that you are dealing with jets several scale lengths, from parsecs to megaparsecs, and with massive black holes in today, right? And also young stellar objects in the way you have spoken about that. Also, at the moment you needed some media inside to take into consideration, just to stop the jet and anything that you have mentioned very well. Mm-hmm. And I wonder, in the starburst nuclear, for instance, you have these superstellar clusters things. There are a large number of simulations, just pure hydrodynamical simulations, in which you get very fancy structures, shells, sort of jets. And at the end, if you have an initial mass function happening in each one of these superstellar clusters, you may end at a given stage with a massive or not so massive black hole in some of them, maybe not in the whole population in the nucleus of a galaxy, but you will have all the ingredients that you are playing with, or many of them, but in a system which is already stratified in a very pretty manner, let's say. So you will have big bubbles, some of them kiloparsec size. Right. You will already have these Rayleigh-Taylor clumps which are inside. You will have a medium which is very hot and very metallic inside the bubbles. Mm-hmm. And for instance, to produce a supergalactic wind, you need to pinch the bubbles somehow and to be able to break these things so as to get everything inside. And to get there is easier because you have something which is very empty, the low density medium, very hot medium. There you can generate a jet very easily, the sort of jet that you are producing. So the question after that is, how difficult would be to take into account these configurations resulting from the hydrodynamical simulations, and to have that as a starting point in your model and in this galaxy to produce a jet and see what happens. And the second question, how difficult would it be to follow the particles so as to be able to distinguish between the metallic ones and the poor, less metallic, classical interstellar medium thing?
Let me try to answer your first one, because that I may have a somewhat reasonable comment to. I think it's a matter of scales, what I'm looking at here. So again, the advantage of having this fluid type viewpoint of it is that, you know, I have just to deal with the local density and the local velocities, and that is in essence just what sets my initial conditions and my simulations, as you realize. Translated then to overall scale, as I said before, the jet conditions that I then typically start with are reminiscent of what we induce from jet radii, jet speeds, etc., at about a parsec or so away from the jet region. And then you may correct me if I'm wrong, but that already sets a certain relative scale to what we can capture in these things. We have a certain resolution then throughout the jet beam radius, which is in our simulations fairly high because of this whole dynamic adaptivity. In fact, in many of the competing simulations, they are quite happy with just 10 or at most 20 or so grid points through the jet beam, so over that half or 1 parsec. We throw in about 100 parsec, but everything coarser than that, we obviously then don't capture, or we have to do something, you know, fiducial. What we could do, and what has been suggested also by others, is indeed the effect of the additional mass that in these starburst regions. So we can somehow also treat that as a factor that is probably quite important in terms of the mass being fed to these jets, which for all intents and purposes now we just take one number and stuff it in our domain. But we should probably do better there, and along the path of these jets prescribe some sort of well parameterized mass feeding, mass source distribution as a function of space and time. That, well, I'd be happy to learn about what kind of numbers I should actually put there. And indeed, we can then try to address these topics in addition, as they make their way through, how the pre-existence or the dynamic formation of these localized features will, in addition, modify these things. Now, the only thing that we did is we kind of invoked those arguments to say that, well, they will traverse through different regions of influence, and hence they will encounter density discontinuities, but admittedly, it's a poor man's solution to the real thing. The last question is much more difficult, again, because of our viewpoint of just the overall fluid view that we have. We have then, in essence, just one quantification of pressure density without any meaningful statement on, you know, the separation between the species. So that, I must admit, I would have to think much harder on how we can even come close to a better quantification of that.
Okay, any more questions, comments, suggestions? Okay, I just remind you that we have a coffee break pretty much right now in the cafeteria, and I think we should thank again Rony for a really nice talk.
Okay.